So our project is on quantum computing. So we are DL2 Red, Why Quantum Machine Learning Matters. My group members are Christopher Dargan, Hyunmo Kim, and I'm Patricia Amel. So first, we're going to start off a bit about classical computing. So classical computing, which is the norm for computers nowadays, operates on a binary system. This binary logic is at the heart of all classical computational operations. The architecture of classical computers is based on the von Neumann model. In this model, a CPU executes instructions stored in memory. This separation of memory and processing allows for the step-by-step execution of instructions, which forms the foundation of modern computing systems. Classical computing encompasses a rich array of algorithms. There are sorting algorithms like quicksort and merge sort, which enable efficient organization of data, and there are searching algorithms such as binary search, which facilitate rapid retrieval of information from large datasets. While classical computing has proven incredibly powerful and versatile, it does face limitations. Certain complex problems, like large-scale factorization or simulations of quantum systems, can be computationally infeasible for classical machines due to their sequential processing nature. Quantum computing represents a profound departure from classical computing. At its core, quantum computing leverages the principles of quantum mechanics. One key concept is superposition, which enables quantum computers to process a vast number of possibilities in parallel. Another crucial principle is entanglement. When qubits are entangled, the state of one qubit instantly influences the state of another, regardless of the distance between them. This phenomenon unlocks a unique form of correlation that classical systems cannot replicate. In addition to these principles, quantum computing introduces quantum gates and operations. These are the building blocks of quantum circuits, analogous to the logic gates in classical computing, and are what enable the execution of quantum algorithms. A quantum algorithm is a step-by-step procedure where each of the steps can be performed on a quantum computer. There are many different quantum algorithms. One notable example is the Deutsch-Jozsa algorithm, which makes it possible to determine if a given Boolean function is constant or balanced. It was the first quantum algorithm to show a separation between the quantum and classical difficulty of a problem. Now that we learned a bit about each of these separately, what are some of the similarities and differences between them? While both are involved in information processing and can perform mathematical operations, the underlying mechanisms and capabilities are fundamentally different. Classical computing operates sequentially, performing one operation at a time. In contrast, quantum computing capitalizes on superposition and entanglement, enabling exponential parallelism. This means that quantum computers can explore an enormous number of possibilities simultaneously, providing a potential advantage for certain types of computation, such as factoring large numbers or optimizing complex problems. It is important to note that the complexity of quantum algorithms and their practical application is an ongoing area of research. Quantum computing is not a one-size-fits-all solution and is still evolving, but it does have a growing potential for solving specific types of problems, which is exciting to see.
Hello, my name is Christopher Dargan, and I'm overviewing some of the basic principles and fundamentals of quantum computing. So, what is the basic unit of information in a quantum system? That would be a qubit. But before looking at the mathematical definition of a qubit, it's good to compare it to classical bits. So, a classical bit is the basic unit of information in a classical system. As you know, classical bits have a limited possibility of states being only two, either a 0 or a 1. And when relating these states to quantum systems, it's good to represent them as vectors. So if we see here, um, the state 0 can be represented as the vector 1, 0, and then the state 1 can be represented as the vector 0, 1. It's also important to note these are determinate by nature, meaning they have discrete predetermined values. On the other hand, qubits, they are non-deterministic by nature, meaning there's no predefined value to them, meaning they can have infinite states or possibilities. And this is in part to their ability to utilize the superposition of classical bits. You can see this in their vector representation. So if you look down to this formula here, psi represents a singular qubit, and the formula is comprised of the two classical vectors 0 and 1, expanded out here, and then they're multiplied by two scalar values, alpha and beta. So alpha and beta are generally complex numbers, as you can see by the imaginary number I in its exponent, and then these scalar values help uh, determine the probability of what qubit um, will be composed. So, like I said before, qubits are indeterminate by nature, meaning they have no intrinsic value. And like I said, in part, this is because they utilize the superposition of classical bits. This is where you usually hear the saying, a qubit can either be a 0 at the 1 at the same time, which is technically true. While operation and gates are being applied to qubits, the qubit fluctuates between having a probability of either being a 0 or a 1. So until that qubit is measured, it fluctuates probabilities of the two possible states. However, when a qubit's measured, it always collapses down to a discrete value, 0 or 1. So below, you can see the qubit here is a visual representation of uh, what the qubit is being measured as. So here, the qubit's being measured as a 0, meaning it has a high probability of that qubit being a 0. Uh, Same thing on the right side. The qubit has a high probability of being a 1. So when that qubit's being measured, it would come out as a 1. However, qubits really want to be that special if they can only be measured as 0 or 1, hence the superposition of a qubit. So, to see the concept of superposition a little better, uh, we have a screenshot of IBM's Quantum Composer, which is a program that allows you to run quantum algorithms. And essentially, here we have a singular qubit. And like I said before, when you apply operations to that qubit, here we have an H gate being applied to the qubit. That qubit is now fluctuating between the states of 0 and 1 once this operation is performed. And then each operation has different effects on the qubit, and we will explain what these operations are later. But here we can see once that gate is being applied, the qubit now enters a state of fluctuating between 0 and 1, while it's having a probability of 50% of being a 1. And then same thing over here, has a probability of being 50% a 0. This also can be visualized over here in the sphere, where you can see the qubit not necessarily pointing in one direction, meaning its possibility of it being a 0, and it also has a possibility of it being a 1. And then this kind of highlights the idea of superposition, where the qubit isn't necessarily one distinct value. It's a probability of either being a 0 or a 1.
Hi, my name is Hyunmo Kim, and I will go over how does quantum logic gates work. Before we go into the quantum gates, these are the basics of classical computing. We use bits as a fundamental unit of information represented as 0 and 1s. These bits can be manipulated using gates to construct circuits that perform various computations. In quantum computing, we replace classical bits with qubits. Unlike classical bits, qubits can exist the multiple states simultaneously with principles of superposition and entanglement. Quantum gates are used to build circuits with qubits. This is an example circuit involving 4 qubits and various gates. After I explain some of these quantum gates, I will show you a demo of how this first single qubit evolves through these gates. To explain how a qubit goes through the gate, I will use this blue sphere that can help us visualize transformation of a qubit through these gates. Blue sphere has 3 dimensions, x, y, and z, representing different aspects of a qubit states. The z-axis expresses 0 and 1, and the x-axis indicates the phase, positive and negative, and the y-axis is plus I and minus I. Also, the vector of qubit will express the probability of measuring 0 or 1. So in this case, this is closer to the 0. So the probability of measuring 0 will be higher. And when the vector is in the middle of 0 and 1, it will measure 50% of 0 and 50% of 1. While the blue sphere provides an intuitive picture of qubits, the actual transformation involves the complex matrix multiplication between the gate and qubit vector. In the subsequent slide, I will go into specific quantum gates and see how does it manipulate the qubit state. These are the single qubit gates. The Pauli X and Y Z gates will have a rotation of 180 degrees around x-axis, y-axis, and z-axis. So for this one, when the qubit vector is initialized to 0, and after it goes through the x gate, this vector will rotate 180 degrees like this. And this vector goes through the y gate, it will rotate like this. And this vector will rotate 180 degrees based on this z-axis like this. And these are another single qubit gates. First, Hadamard gate will also rotate the qubit 180 degrees around the x equals z line. So this is the x-axis and z-axis, and x equals z line will be like this, and the vector will rotate 180 degrees around this line. So this vector goes after Hadamard gate, it will rotate like this, and S and T gates will make the vector rotate 90 degrees and 45 degrees around the z-axis. So this will be rotate 90 degrees, and this after the T gates, it will rotate 45 degrees like this. Now these are the multi-qubit gates that work with more than two qubits. This is the CNOT gate. In this circuit, the CNOT gate influences the target qubit based on the control qubit state. If the control qubit is 0, there is no effect on this target qubit. But when the control qubit is 1, it will affect to change 0 to 1, and if it's 1, it will make it to 0. And CZ gates operate on a similar principle, but change the phase. So if it's 0, it wouldn't affect anything, but when the control base is 1, it will change the phase plus to the minus. So when it's minus, it will go to the plus. So to tie it all together, let's see a demo of a simple 1 qubit circuit. Starting with this qubit initialized to 0, we'll apply to Hadamard gate and the Pauli X gate and another Hadamard gate. After go through these gates, this will measure the qubit state. So if I play this video, it initialized to the 0, and after we apply Hadamard gate, this will be rotate to here. And since it's on the x-axis, even if it go through the x gate, it will not change anything. And from here, after it goes to the Hadamard gate again, it will move back. So after this and measurement, we'll find 100% probability of measuring 0.
So to demonstrate quantum algorithms a little better, we wanted to demonstrate how quantum algorithms can compare and surpass classical computing. And here we looked into Deutsch-Jose's algorithm. So this algorithm considers the following problem. Consider you had a function f of x, and suppose this function was a black box sort of algorithm where its input is just n bits of strings, and it can only return a 0 or a 1. In quantum computing, this black box algorithm would be called an oracle. So consider we want to define this function as being constant or balanced. If the function is constant, it returns all the same values for any input. So it either returns all zeros or all ones. If the function was to be considered balanced, it would return exactly half those same values. So exactly half the values would be zeros and exactly half of your values would be ones. So you can see this by the truth tables here. If the inputs were 0 and 1, a constant function would return all zeros. If it was a constant 1 function, it would return all ones. And an example of a balanced function would be a NOT gate. So if you had the inputs 0, 1 and a NOT gate applied as your function, zeros would be mapped to 1, 1 would be mapped to 0, and it has exactly half the values, meaning the function is balanced. So hopping over to IBM's Quantum Composer, we see here that we have a smaller version of Deutsch-Joseph's algorithm. We have 2 qubits, and we have a wall of H gates. Here we have our black box function. Here it would be the identity gates being applied, and we want to measure the qubits at the end. A little precursor. These gates being applied zero out these qubits, meaning the function will always output a 0. Hence, the function is constant. So Deutsch-Joseph algorithm essentially determines that. So if we set up and run this circuit, we can see that it produces a outcome or the bit as 0. And if we look back, a 0 means the constant or the function is constant, which is true because the identity gates would just output a 0. So looking at another function, this is a bit of a more complex circuit involving 4 or 5 qubits. And here we have our wall of H gates. Inside of this would be our black box function or oracle. And then we want to measure these qubits at the end after H gates are applied. Here we have a series of NOT gates, and essentially these NOT gates produce a balance function where half the qubits are mapped to zeros and half the qubits are mapped to ones. And that can be seen if you mapped out the truth table for the circuit. And essentially, if we run this, we can see the probability is mapped to a 1. And then, like we said before, if the output of the algorithm is a 1, that means the function is balanced. So this function here is a balanced function, and it determined it in a time complexity of 1 compared to an iterative process in classical computing.
So in our presentation, we compared the classical computing and quantum computing, emphasizing the game-changing role of quantum bits with their ability to exist in multiple states at once. We explored the Deutsch-Jozsa algorithm and the power of qubit superposition. The shift from classical gates to quantum gates was highlighted, showcasing the transformation nature of quantum operations. The Blow-sphere was introduced as a visual aid, making complex quantum concepts more accessible. And thank you for watching our presentation.